Welcome to the second screencast for Chapter 9, dealing with gases. Let's pick up where we left off after the first screencast, and now we'll look at a different pair of variables, this time volume and pressure for gases. And it turns out that when we decrease the volume of a gas, we find that its pressure increases, provided, of course, we keep the temperature and the amount of gas constant. And if we increase the volume of the gas, we find that its pressure decreases. And if we graph a series of data points for a sample of gas at a constant pressure, we see that the pressure-temperature curve looks something like this, which looks an awful lot like inverse proportionality. This is something that was done with the syringe in lab. And when we do our careful experiment and get this graph of pressure versus volume, we note that P is in fact inversely proportional to V. When the pressure goes up, the volume goes down. When the pressure goes down, the volume goes up. That's inverse proportionality. If we go through this process and note the mathematical relationship, it's called Boyles Law, and it states that for a fixed amount of gas at a constant temperature, the pressure and the volume are inversely proportional. How we can write this is P equals some constant K over V, or P times V is equal to the constant K, so pressure times volume for state 1, P1 times V1, equals pressure times volume for state 2, P2 V2. And we can apply this to some examples. So, for example, at 25 degrees Celsius, we have air in a syringe at a pressure of 1.5 atmospheres. If we decrease the volume, we expect the pressure of the gas in the syringe to increase. And if we increase the pressure to 3 atmospheres from 5 atmospheres, what would the volume be under this set of circumstances? And we note that a pressure increase from 1.5 to 3 atmospheres is increasing the pressure by a factor of 2. And since volume is inversely proportional, what we expect is that the volume will decrease by a factor of 2. And so we go from whatever, and it wasn't stated in the problem, so let's say we start with 60 milliliters of air in a syringe, then it would go down to 30 milliliters of air. When the pressure is doubled, the volume is halved. Here's a more concrete example. If any of you are scuba divers, I happen to like scuba diving, and especially if it's in tropical water. So my daughter Sarah is a scuba diver as well, and let's say that she has a lung capacity of about 4.7 liters at sea level. Now when you dive, you're underwater, you're at a much higher pressure, and it happens that every 33 feet or so underwater you go, that's an additional 1 atmosphere or so worth of pressure. So if you start with 1 atmosphere of pressure at sea level, 33 feet underwater is a 2nd atmosphere, 66 feet under is a 3rd atmosphere, and then at 70 feet the pressure is about 3.1 atmospheres. So what happens is, here's our initial state, a representation of Sarah's lungs, and at a lower pressure, when we're deeper underwater, basically the lungs get squished down to a smaller volume. So our data is 4.7 liters at normal atmospheric pressure of 1 atmosphere. Scuba divers breathe compressed air, and in this case the pressure of the air would have to be at least 3.1 atmospheres for the diver to be able to even get the air into the lungs. And what is the volume now? What's happened to the volume of the lungs? Well, that's what we're going to try to find out. Boyles' law says P1 V1 equals P2 V2. V2 is what we don't know, so we'll solve for V2, and it's equal to P1 times V1 over P2. And if we plug in our values, 1 atmosphere times 4.7 liters divided by 3.1 atmospheres, and note the volume would be expected to go down by something like a factor of a little over 3 because the pressure went up by a factor of a little over 3, and that turns out to be 1.5 liters, pretty much as expected. Now it turns out that we have similar relationships to the ones we saw in the first screencast between pressure and temperature and volume and temperature, and now in this screencast between pressure and volume. And it turns out we can do relationships between volume and amount of moles, which is called Avogadro's law, and any other pairing of quantities or variables we want to do. And it turns out that if we do that, we can lump all of these individual gas laws together to get two things. One is known as the combined gas law, and the other is known as the ideal gas law. The combined gas law is that P1 V1 over T1 equals P2 V2 over T2, and for that matter we could also throw in an N1 over here and an N2 over there, but usually we're not changing the number of moles. We have a trapped sample of gas and we change its pressure, volume, and or temperature, and so usually this is sufficient, but I should note that technically we'd have N1 over here and N2 over there. So that's the combined gas law. And note, if the pressure is constant, then P1 and P2 are equal to each other, and it's kind of like we cancel them out of the equation. So we have V1 over T1 equals V2 over T2, one of the gas laws we saw previously, Charles' law. If volume is constant, then V1 and V2 are equal to each other, and that means that the combined gas law reduces to P1 over T1 equals P2 over T2, another gas law we've already seen, i.e. Gay-Lussac's law. And if temperature is constant, then T1 and T2 are equal to each other and cancel out of our equation. We have P1 V1 equals P2 V2, which of course is Boyles' law. Now we also have what's known as the ideal gas law, which is a relationship between the pressure, the volume, the number of moles, and the temperature of a gas. And this summarizes all of the individual relationships, such as pressure and temperature are directly proportional and pressure and volume are inversely proportional. And it has an explicit constant, R, which is the gas law constant, the ideal gas constant, which has a value of about 0.0821 liter atmospheres per mole Kelvin. And that's the same value for all gases that are ideal. And this is a sort of hypothetical kind of gas that is only approximated by real gases, but if the pressure is reasonably low and the temperature is not too low, then real gases are pretty well approximated by this relationship. Now we can use this to solve problems, a little more general problems than in the previous examples. So let's do hopefully two in this screencast before we run out of time. The first one is weather balloons can go up into the atmosphere if they carry, and they can carry an instrument package to study the atmosphere and weather, but the gas in the balloon needs to be less dense than air. So let's suppose that the gas we're using here to fill the balloon is helium. It's filled to a pressure of 720 millimeters of mercury at 22 degrees Celsius. The question is, what's the volume of the balloon? And note, we know the amount of the helium, and it's pretty simple to convert that to moles, which is the units we're going to want to use. We know the pressure of the helium, and just as a note, there are 760 millimeters of mercury in one atmosphere, so we can convert the 720 millimeters of mercury into atmospheres, and it's 0.947 atmospheres, and we want atmospheres because that's the units that R is in. And then the temperature, of course, needs to be converted to Kelvin. 22 degrees Celsius plus 273 gives us 295 Kelvin. And the volume is the only one of the four quantities or variables we don't know, so we can solve for V using the ideal gas law. We know P, we know N, we know T, and R is a constant, so of course we know that. That means the only thing we need and don't know is V. So V is equal to nRT over P. And if we plug into our equation our numbers, excuse me, we have 3875 moles times 0.0821 liter atmospheres per mole Kelvin times 295 Kelvin divided by 0.947 atmospheres. Moles cancel, atmospheres cancel, Kelvin cancel, leaves us with liters, and we plug in all of our numbers and then round off to 3 significant figures, and we get about 99,000 liters. So pretty big balloon to carry up our weather package up into the atmosphere. All right, last one for this screencast. Suppose that we have an automobile engine, and how these work is, of course, there's cylinders in the automobile engine. They take in air, compress the air, and then inject gasoline, light the gasoline with the spark plug, and then the explosion or the rapid burning of the gasoline with the compressed air gives off energy, which expands the piston, and then that eventually is turned into mechanical energy to move the car. We're going to just simply look at the compression part, and so we start with a volume of 400 centimeters cubed. The air comes in at 1 atmosphere and normal atmospheric temperature, in this case of 20 degrees Celsius, and then it's compressed to 50 centimeters cubed, so much smaller volume, and then the engine is hot, so the air heats up as well, so it goes to 450 degrees Celsius, and the question is, what's the final pressure of the gas in the cylinder? Now note, the volume goes down by a factor of 8, so we'd expect the pressure to increase by a factor of 8 just due to the volume change itself. And then the temperature goes up, well, let me see, from 20 degrees Celsius to 450 degrees Celsius. Remember, we have to deal with this in Kelvin, but it's going to be something like almost 300 Kelvin to over 700 Kelvin, so it's going to go up by a factor of more than 2 for the temperature. So we'd expect just from the temperature aspect the pressure to more than double. So we're going to have an 8-fold and then more than double increase in pressure. So we might expect the final pressure to be pushing something like 20 atmospheres. Let's calculate it explicitly and see what we get. So there's our initial conditions. Squeeze the gas down to a smaller volume, heat it up because the engine is hot to a higher temperature. We know all of our values except for the pressure in state 2. So P1V1 over T1 equals P2V2 over T2. Plug in our values. And then it should be fairly easy to do the math. Multiply both sides by 723 Kelvin. Divide both sides by 50 cubic centimeters. And hopefully you will agree that that gives us 19.7 atmospheres, not too far off from the something like 20 atmospheres we were guessing based upon the effect of an 8-fold increase in pressure due to the volume decrease and more than 2 factor increase in the pressure due to the more than 2-fold increase in the temperature. And that's a good place to stop Screencast 2.